about soils. It's one of my great passions in life. I think it's a just like a really neat subject, and I'll talk a little bit more about why, because there's just so much science going on with it, and I just find it really interesting. I love that everyone's putting in where they're at in Illinois or wherever, because I saw that a couple of people registered from across the country as well. So feel free to keep doing that where you're at. If you're a master gardener, master naturalist, feel free to do that as well. Love to see it. We love to hear where you're coming from. So today we're going to be talking about soils, and just want to get my video so I kind of can see a little bit, and soil science and ecology. And you're here as part of the Everyday Environment webinar series. As Val said, make sure you keep your videos off. Val is going to be kind of our tech person today. So if you find yourself accidentally unmuted or something, Val might mute you if that comes up, if it ends up kind of causing some feedback or whatever. So it's not a ghost, I promise, it's Val. She's also the woman behind all the emails and my wonderful coordinator. And so anything like that, and she'll help us monitor the chat as well. We'll probably have some time for questions at the end. So I'll probably answer a lot of those questions at the end, because a lot of the answers might come up later in the presentation. And so kind of keep that in mind. I also want to note that I put the evaluation here as in case, you have to log off early, or if maybe you log off because you're like, this isn't for me, or if you get kicked off like I did. I have a backup plan for that, by the way, if that happens, but always fill out the evaluation either way. If you left early, we want to know, that you had to get going or that you didn't want to be there anymore. That's information that's really valuable to us as well. So I'll get us kind of started. I put this slide in here because this presentation is actually based a lot off of my soil science and ecology video that I made for the Master Naturalist training. So if you're a Master Naturalist or you've seen that 1 hour video, some of this content may seem familiar. It's definitely been worked a little bit to talk more about the building of soils and how we can apply this knowledge in our own landscapes. And there's some more condensed pieces, but if you're like, this looks kind of familiar, I may know what this is already, this is kind of why. It's because it's a lot of it based on some of the content that I've already developed for the Master Naturalists. So today we're going to be talking about 4 basic topics. The title of this webinar is Building Better Soils. And I think it's important to note that we can't build up our soils if we don't know what's going on in them. And so how I really approach this topic is talking about, how our soils are formed and what's going on with them, so that way we can learn the lessons that our soils are already doing and use that to apply how to build our soils. And so I'm going to be giving you concrete ways that we can build up our soils, but I want to make sure that you have the foundation and the understanding of how those soils are functioning in the first place, so that way you understand the why behind what we're asking, but on the what. And so we're going to be talking about the origins of soil, the physical and the biological properties of soil, and then we'll finish with building up our soils and a little bit of assessment soil, how to assess our soils as well. So I want to make sure we're all on the same page with what the heck is soil. Soil is the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of plants. So if you came here today because you were like, oh, how do I, have the best growth medium for my potted plants? What do I buy? What do I mix it with? Things like that. That's not really what we're talking about today. We're talking about native soils, the soils physically beneath our feet, and not exactly about growing mediums that we create or can buy or build from the store. And so I really want to make sure I clarify that's kind of the expectation of what we're talking about the rest of this hour, is these native soils, these natural soils, and how we can build them up, or what we can learn from them even. Now, when we break down native soils into their components, I'm also going to be talking about there's two kinds of native soils. There's organic soils and mineral soils. I'm going to be talking about mineral soils today because that's a majority of what we'll see in our landscapes and what you're probably trying to build or trying to affect. And so those are typically 45% mineral materials or rock particles. And 5% organic matter, or sometimes even less, depending. Soils that are higher than 5% organic matter are what we call organic soils. They're like wetland soils. They have a lot of really different properties. And it's not typically what you're going to see like in your yard, for example, because we're not building houses on wetland soils because they're not a very good foundation. I really love this image of the components of soils from the University of Hawaii because it gives this little zigzag line here between air and water, which I think is so important because it shows that the percentage of air and water can really shift depending on the weather, depending on the day, things like that. And you know, what we do with it. And so I think it kind of shows this fluidness. Val, are we recording? I forgot to hit record.
I am recording. Yes.
Oh, lovely.
You are
Thank you,
being
Val.
recorded.
Awesome. Okay. um, so based on that official definition and the components of soil, something that I think is really beautiful and the reason that I love soil so much is that I really like that it's this meeting of biology and geology, how our soils are formed, and the physical factors are really this geological component, and thinking about, you know, our landscape on this kind of geologic scale. Biology is so important and essential to our soil. It's the medium for growth. It's where a lot of nutrient exchange happens, things like that. And so I just think it's this kind of a little bit poetic to think of it as this meeting of biology and geology if you have that kind of passion. And so that's why I like it so much. So I said we're going to talk about the origins of soil. And when we talk about origins, we're talking about the forming factors. There are 5: climate, organisms, relief and topography, parent material, and time. And if you're like, that seems like a lot of things to remember, for some reason, in education, we decide that the 5 forming factors, the acronym to help us remember is the word CLORPT. I don't think that's a real word. I think that's just there's one vowel and they were like, that's the best we can come up with. But that's just kind of, if you're like CLORPT, that's what are the 5 forming factors? That word kind of helps you remember. We are not going to talk about them in this order specifically. I'm actually going to start with parent material because that's kind of the basis for what we're working with. So when it comes to the soil forming factor, the first one, parent material is the geologic material from which soil was formed. So there's quite a few options here. We have glacial formation. So this is a picture of glacial till. There's also outwash. We have parent material that's just from gravity. We call that colluvium, materials that have actually been moved from one space to the base of a hill due to their gravity. We have wind, which is loess. There's also another wind parent material called Aeolian sand. It's like really, really small sand. There's also just local bedrock, what was there originally. Southern Illinois has some really wonderful local bedrock features in Garden of the Gods and Shawnee National Forest. And then there's water moved transported materials as a parent material, and we call that alluvium. I like this image because it kind of shows like the water being like physically how the water moved it, because that's that stream right there. In Illinois, though, much of our parent material is from glaciers. And this is a good map to show us like how much of Illinois was actually glaciated at one point. So the Illinoisan glacial period covered most of Illinois and left just like this northwest region and the most southernmost tip of the state as unglaciated. The most recent event was about 15,000 years ago from the Wisconsin glaciation. It covered much of northern and east central parts of Illinois. And glaciers in general, no matter what event it was, are quite violent forces of nature. They'll scrape and take in land materials as they move across the land. And then as they recede, the meltwaters leave behind whatever they picked up. So they'll leave like large landforms or rock materials. And that's what forms our Illinois soils. And not only did the glaciers cause these rock materials, but also some windblown materials due to the climate of that time. And that's what we call windblown silt from glaciers is called loess. Rhymes with bus, but it's spelled Loess. And much of Illinois soils are actually loess. There's this, you could probably find, I can't remember exactly who the source is, but there's like a really good loess map somewhere that shows you like this area has 20 feet of loess. This area has like just a couple inches. But a lot of Illinois soils are like loess over glacial till or something like that. And loess is just this really great like silt, like middle of the road size particle that is just really great for a lot of reasons. And we'll talk about that when we talk about the physical properties. But it kind of is one of the reasons, one of many, that, you know, Illinois is part of the breadbasket of America, what makes us so good at growing things in Illinois. So now that we know what we're starting with, which is our parent material, we also need to introduce an important concept that impacts the rest of our soil forming factors. And that's this idea, this concept called weathering. Weathering is the breaking down or dissolving of rock or mineral particles on the surface of the earth. And weathering can be influenced by a number of factors. It can be physically from water, ice, and temperature, chemically from acids and salts, to biologically from animals and plants. And so this image here shows you like how the process of weathering kind of occurs and forms soils. So we start here with rock on the left. It rains and water kind of gets into the cracks, freezing and thawing. Maybe some expansion occurs from the freezing and thawing of the water, causes more breakage. Organic matter becomes introduced, and that causes more dissolving and breaking down. Now there's chemical processes occurring maybe that were picked up by the water and the rain. Dissolving things like that to form a fully well-developed soil over time, because there's this weathering that's occurred, this breaking down or dissolving of materials. And this weathering, like I said, is influenced by a lot of factors, and that's kind of how we come up with our soil, the rest of our soil forming factors. The next one of which is climate. So those are the weather conditions prevailing in an area over a long period of time. Illinois climate is temperate with a variation of wet springs and winters and dry summers and falls. And since the deposition of our parent material, the soils have been freezing and thawing seasonally. And we've also been seeing saturation and drying out depending on the area. And this has caused weathering of our soils. So these maps here are actually from the Illinois State Water Survey of the last 200 years, which is not a very long amount of time for soil formation, but it just kind of gives you an indicator that we see this even annually, these large changes. If you look at the blue lines in temperature, average temperature for a whole year, we see large changes in annual precipitation over time. And this isn't even showing seasonal changes. And so this is causing some really decent weathering for our soils in Illinois. Another important soil forming factor is time. Just to kind of put it in perspective, it takes about 300 to 500 years to form 1 inch of topsoil. So that's just topsoil that we're talking about. But if we talk about the whole soil profile, time makes a really big difference. So this image here shows 2 very different soils. The soil on the right is the state soil of Illinois. This is Drummer Silty Clay Loam. Fun little bar trivia fact for you if you like. And the soil on the left is the state soil of Georgia. This is called the Tifton series. It's formed under marine sediments. Drummer soil is formed under loess. That's its parent material. And the Tifton soil is much older than Illinois soils and our Drummer. And it gives us a really good indicator of age. It's just had so much more time to weather and oxidize, to leach out. and for more chemical processes to occur. And so oftentimes you can actually physically see this difference if you drive south, head to Arkansas, Georgia, Texas. And if you see areas where there's no vegetation, the bare soil, it might look really light, maybe a really tanner color. You might also even look red, red dirt clay. That's what they're talking about in all those country songs. It's a lot of the times because of the age of that soil. Our next soil forming factor is relief or topography. That is the arrangement of features on a landscape, so physically where it is located. This hill on the left, for example, when rain goes down or when rain comes, water is going to hit the surface of the hill. Let's imagine a raindrop hit the top of the hill. Right here. I don't know why I'm pointing with my camera because you can't see what I'm pointing at. But it hits the top of the hill and it's going to pick up debris and sediment, and it's going to run down the hill and settle at the base. The soil at the top of that hill, due to that water hitting the top and running down to the bottom, is going to be very different than the soil at the base of that hill. And the same as the soil that's maybe on the slope as well. And so this can cause just different soil profile makeup. It can also cause, like this image on the right, some pretty extreme erosion events as well, depending on where your soil is physically located on the landscape. And there's a lot of other factors here as well, but where it is physically located matters, is what I'm trying to say. And this reminds us of a really important factor when it comes to soil and geology, that water is the most powerful force on Earth, the most powerful natural force on Earth. Wind can really only take something that is light enough to be carried by it. I know we have like really, we can have really extreme wind events and things like that that can carry large, heavy things. But water has this really, really skilled ability to force the smallest sediment to the largest, move large boulders, carve out lakes and canyons. When it freezes, it physically picks things up and moves it. And it's formed a lot of the landscapes that we know today. If you're ever wondering, what happened here? Why is this hill? Things like that. My first question is like, well, what's happening with the water, or what has happened with the water? When I get calls from people about what's going on with my yard or whatever, my first question is what happens after it rains, or what happens when it's raining, because water really does shape a lot of our landscapes. And it's shaped a lot of our human decision making as well. When we think about where we've settled our cities, where we put certain spaces, why we have to build certain things in certain ways. A lot of it has to do with water. So we really need to always be thinking about that factor when we're asking questions about the landscape, is, well, what's happening with the water, or what has happened with the water? So our last soil forming factor is organisms. So this could be anything from microorganisms to plant vegetation, to macroorganisms, fungi, whatever. Every living thing can affect our soil and how it's formed over time. And so this image here shows you a difference of vegetation and how the soil just physically looks different because of the difference of vegetation that has occurred there. So this image on the left, the soil formed under mainly grass vegetation. The soil on the right formed mainly under forest vegetation. There's a specific order of soils called spodosols that are typically formed under very like acidic, like pine trees, things like that. And they have like really, really cool soil profiles. And it's all because of that acid reaction that's occurring from the pine needles dropping, or from the conifers. And so we're going to talk a lot more about organisms and biology, but it is a really important soil forming factor that can form very, very different soils. Okay. So we talked about formation. Now we're going to talk about the physical properties, what we're physically seeing in the soil. These are things that we observe from a soil sample. This image here is a really great example of what we see. So this is these two soil samples were taken from the same physical location. These are actually from Champaign, in one of the soil pits on the South Farms, if you're familiar with that space. And this is taken from the surface, this top one, and this one is taken from the subsoil. And so you can see here by looking at this that these are two different colors physically. These are different arrangement of particles. So these are more broken up, smaller pieces. This is a larger chunk. And then if you were to physically feel the soils, you would be able to see that these soils physically feel different. One will feel softer or grittier or something like that. So when we talk about the physical properties of soil, this component, we're really talking about the 45% mineral particles. And we're going to discuss the implications on these mineral particles on the organic matter and the water in the air. So we'll kind of talk about what all of that, how those things interact. So we're going to focus on three main physical properties of soil: texture, color, and structure. And each of these physical properties tell us a lot about what's going on beneath our feet. So when we talk about texture, we're talking about the different sized particles that make up the soil. Those three particles are sand, our largest, silt, the middle one, and clay, the tiniest. And what I want to clarify is that when I talk about and use the terms sand, silt, and clay, the difference between these three particles is size. Sand is defined by a certain size, clay is defined by a certain size. I'm not talking about, that they're there's different chemical properties based on their physical size. That's how we define them. That sand is anything that's 2 to 0.05 millimeters in size. That's all we're talking about here when we say sand. And because of those physical sizes, there's some really interesting properties that go with that. But I want to clarify that it's not, we're not talking about, different rock makeups. We're talking about just physical size of a particle. We're working with these really small sizes, and it can seem really, really confusing. And I kind of threw out that number about what size sand is. So I thought it would be helpful to give you like a metaphor for comparing them, right? So if sand itself is 2 to 0.05 millimeters, and if we were to just say that sand represented something, sand represents a beach ball. We're just going to call it this relatively large particle size, a beach ball. If we were to compare sand to silt, comparatively, silt is about the size of a marble. So the sand is much bigger of a particle than our silt. And then if we were to compare that to clay, clay is the size of a pinpoint, even smaller than our marble, even smaller, especially than our beach ball. So we're talking about three very, very different sized particles here. And that's why they have some unique properties that go with each of them, and I'll talk about those, but I just kind of feel like it helps to give you some kind of comparison. So sand is our largest particle size. It allows for really, really big pore space because of its physical size. And I included some images here on the bottom that kind of give you an understanding of why sand allows for bigger pore spaces. So if we had a jar of sand, or I'm going to call sand now we're going to call it a ping pong ball. You can see here that this jar here is full of ping pong balls. However, there are air spaces between the ping pong balls. I can't fit any more ping pong balls in my jar, but there is spaces between them. And so that's what sand allows for in the soil. It allows for these larger pore spaces that allow for drainage of the soil. Physically, it feels gritty. When you feel a soil sample with sand in it and you hold it up to your ear and you kind of rub it between your fingers, you can hear the sand. Silt is our middle of the road medium-sized particle. Sticking with this jar example, imagine now we have a jar full of marbles. Our marbles, there's still spaces between our marbles, but our jar is full of marbles. But the space is smaller than our ping pong ball space. So there's still spaces, but they're much smaller. And these pores, because they're a little bit smaller and because of just kind of the size of silt, it has kind of this sponge-like property for water. It allows for the absorption of water. It'll hold on to the silt particles will hold on to the water, but it also is willing to share. It gives it, it's very nice. It's very kind. It gives it freely to plants. And so it's a very favorable particle, which is why when I say loess helps form the breadbasket of America, the wind-blown silt of a parent material, that's because of this sponge-like property. It allows water to be more available for the plants. If you were to find silt in its pure and dry form, which is very, very rare and probably not going to be happening anytime unless you're like in a lab or something, it feels soft. It feels like flour, but that kind of gives you a comparison of like what that particle could feel like. Now, our smallest particle is clay. Keeping with that kind of jar comparison, now imagine we have a jar full of poppy seeds. The spaces between the poppy seeds themselves are much tinier than our marbles or our ping pong balls. So these spaces are so tiny, and because of those really small, tiny spaces, it's actually really hard for water to infiltrate into clay. That's why often, you might hear somebody say, "Oh, I got a clay pan or a layer of clay beneath, a couple feet down, and so water just pools on top," or something like that. That's why. It's also the chemist of the soil. So clay particles themselves, because they are so tiny, they have a negative charge, which allows for a lot of nutrient exchange, a lot of chemical processes to occur. And also that negative charge means that it adheres to water molecules more tightly. So it doesn't like to share water. It's not a very good, it's not as kind as silt, you might say. And so that's why oftentimes, clay isn't a super favorable particle to have like a lot of clay in your soil, if we're talking about plant growing and things like that. However, it is important to have clay because it's the chemist of the soil. It allows for a lot of that nutrient exchange. It feels physically sticky and tough. If you're working with like 60% clay in a soil, your hands are going to hurt. That's just kind of the way it is. Now, these soil particles, these three sizes, don't occur naturally as like 100% clay. You're not going to see just like a silt out in the wild. So what researchers use to define them is this soil texture triangle. Not super important to know unless you're kind of a nerd like me, but essentially it just kind of tells you that, when we have a certain percentage of silt, a certain percentage of clay, and a certain percentage of sand, we might have like a silty loam. What we typically see is kind of somewhere in the middle here. We don't see a ton of like really high silts. Sands you might see in very specific spots. Clays, depending on where you are, could be more common. In Illinois, I would even consider moving this a little bit towards the right, this direction, towards the silts, just because of that loess content we have as a parent material. So, why does this matter? Why does it matter that we have this much percentage of sand, this much percentage of silt, this much clay? Why does it matter that we have these kinds of things in our soil? And that has something to do with water. When talking a little bit about water and its properties, water is kind of unique. It has this cohesive and adhesive property. So I'm going to throw you back to like grade school science class a little bit. So cohesion and adhesion means that water has the ability to stick to itself and it has the ability to stick to surface. It's those same properties that, when you're baking or cooking and you have to measure a cup of water, and then you remember you go into your measuring cup and there's like a little U formed, that's the meniscus. That is adhesion, that's water sticking to the measuring cup sides. Another little science experiment is when you fill up a cup of water full, and then you add paper clips to it, right? And then you keep adding, and if you can, you keep putting them in until the water spills over. But right before it spills over, you notice that there's a little bubble that almost exceeds the edge of the glass. That's cohesion, water trying to stick to itself. So these properties retain themselves in soil. And so because of that, different soil textures change the water holding capacity, or the amount of water a soil can hold. So this image here kind of shows an example of that. So we have adhesion occurring here, soil or water sticking to the soil particles themselves. We have cohesion, water sticking to each other, their own molecules. And when an airspace is big enough, like with our sand, creating those larger air spaces, we have it's too big for cohesion to occur, for water to stick to itself. But if it's a little smaller, we do have cohesion occurring and water is filling in that airspace. So it allows for different water holding capacities of our soils depending on the texture. And this is kind of, I'm putting it all in silos and really simplifying it, because all of these organic matter, the forming factors, physical properties, they all really do interact with each other to create, different water holding capacities. But if we were to really kind of silo this and say, well, how does texture affect available water? Specifically, this graph is kind of is a example of that, and really kind of showing that different textures, from sand to silt is in the middle and clay is on the other sides. The wider the band here, the more water available for plants. And so we see here that there's less water available for sand because those pore spaces are so big and the water's draining really quickly. There might be more water physically in the soil, but depth, or because clay likes to hold on to water so tightly, it's less available for plants. And so our loam is where we really see it bubbling out. And why does this matter? Well, it might help inform some plant choices. So drier loving plants might be more suited for sandier soils. Nodding wild onion is an example of that. More mesic plants that kind of, I call them mesic, kind of like the Goldilocks of water conditions. It's like not too wet, not too dry. Purple coneflower might like a more siltier, a more loamy soil, that middle of the road particle. And then more water loving plants where water maybe just sits in the soil because of the clay, might like more clayier soils like swamp milkweed. Like I said, this is all kind of in this silo of, like, we're just talking about physical properties, but it's another tool in your toolbox when it comes to understanding your soil and your landscape. So another physical property to understand is structure. That's how our soil particles are arranged physically. There's a few. The important ones to know kind of tell you a little bit about what you've been doing to the soil physically over time. Granular is just kind of how naturally the top soil forms. But if you see platy structure, which is kind of like literally like a stack of plates in your cabinet, in the profile, that might tell you that there's some compaction happening. Subsoils are typically blocky or subangular blocky, kind of like this cube-like. How old this soil is, the more structure it has, the more order it is, and also about some disturbance factors. So structure is coming and going. Val, how am I doing?
Yeah, you're coming in and out. Do we want to stop the recording for a minute and switch over to mine? And you can um, come in with your phone.
Oh, shoot.
Hang tight, everybody.
Really appreciate it, by the way, you stepping in. So thank you. So yeah, so we're talking about structure and the importance of it. This gives it stabilization for growth, for for plants, for our houses, for everything. Structure is really, really important. And to kind of give you an understanding of, you know, what the heck that means a little bit is, imagine the analogy I like to use is cake. So a soil without structure is like a bowl of cake mix, and a soil with structure is like a cake. So if I were to stick my finger in a bowl of cake mix and take my finger out, instantly that soil or that bowl of cake mix is going to fill back in. You're not going to see where my finger was. If I have a cake that I just so rudely stuck my finger in and removed it, you'd see a finger-sized hole. And so that kind of tells us, or that kind of shows us the importance of formation of soil structure itself. And so we really need that structure to be there in the first place. And when we do things like we till it, we're basically breaking up the cake, and we're destroying that soil structure itself that took years to form. And stabilizes the soil itself. So, and we'll talk more about tillage practices and what that does to the soil itself, but that's one thing that it does, is it destroys the structure. Another important physical property is color. So that essentially thinking about the darker a soil is, the brown black color tells me that there's more organic matter in the soil. And then when we think of red and gray as a color, we think of red spots in soil are typically an oxidation reaction. So think rust in Illinois, at least. Red could also mean it's really old, right? Like I mentioned that before, that red dirt clay. But we know that's not the case in most of Illinois, that our soils are not, you know, they're about 15,000 years old. That's relatively young. And so we know that it's typically an oxidation reaction from water in some way, shape, or form. Some soils can have gray spots like this image here as well. And some also, those are called depletions. And that's places where nutrients have left an area due to anaerobic or saturated water conditions. If a soil is entirely gray, like you dig deep enough down, that usually tells you that's where the soil is saturated most of the year, that it's had so much time in these anaerobic or saturated conditions that the soil itself has had the time to do these depletion reactions. And so it's a good indicator of where a water table is. So this image here is actually, I took of an Illinois soil. You can see I'm literally standing in water here at the bottom, and the water table is actually kind of up here. This is grayer right here. So I know, and then this redness tells me as well that there's this oxidation occurring. So now we're going to talk about soil biologic properties, and what we can learn about the biotic side of soil. So when we talk about the mineral portion was 45%, we're now talking about this 5% and how this 5% impacts the rest of the 95% of the soil. And we're going to break that down even further to talk about, you know, a different kind of pie. So this 5% transferred into this bigger pie right here, and tells them that there's all these different components that make up the organic matter aspects of soil. And before we go into those specific components, I want to make sure that we highlight the importance of soil biology. As a whole, it contributes to nutrients. It contributes nutrients to the soil as it decomposes and enables soil to actually hold on to nutrients. It also helps with the structure of the soil. Instead of being so compact, it actually loosens it. If you have a soil with high organic matter content versus loosening it up and allowing for more aeration. It also increases the ability of the soil to hold plant available water. This is why I kept mentioning that when it comes to texture, these things don't exist in silos. They're all interacting with each other. Because just
Abigail, you are breaking up again.
rainfall, topography and slope. But additional natural influences on soil biology include the vegetation of that soil, the texture, the drainage. If the soil is really acidic, it's affecting decomposition rates and things like that. Hey, Val, I think you might need to mute, by the way. There we go. Okay, so, and then there's also human influences on soil. Those are erosion when we remove the top, like the plant cover, or we have construction, we're removing the organic matter as well. Tillage practices as well. The more we beat up the soil, we're introducing air, which actually has an oxidation reaction with the carbon in our soil, and that causes carbon dioxide to be released into the atmosphere. So our carbon, our stabilized carbon, oxidizes into carbon dioxide and is released in the form of gas. Something that has the opposite effect that increases soil biology is cover crops. That's something that's actually like actually adding more carbon, depending on if we're harvesting those cover crops too as well. So getting into those different pieces of our organic matter pie, we're going to talk about first the less than 5% of organic matter, and those are the living organisms in the soil. These are kind of the driver of a lot of the processes that we're seeing when it comes to the living, the organic matter part of our soil. So this can be anything from plant life, microorganisms, of the bacteria and fungi to macroorganisms such as insects and other animals. This is an image from the Field Museum's Underground Adventure. I just think it's really cool because it shows that, you know, we learned about food webs growing up, but to see them in the below, like what happens beneath our feet, just really kind of shows us the complexity of it all, which I think is really, really valuable. So now we're going to talk about the stabilized organic matter portion of the soil. This is otherwise known as humus. It's not humus, it's humus. It's a large portion of the biological part of soil, and that's what gives the soil this really dark, rich color. So again, I kind of show you this image here of the soil I collected from Champaign. This is the top soil. It has a much higher organic matter content than the bottom. And humus allows for improved plant growth. There's really a more water holding capacity for the humus. It gives it the sponge-like property, the soil, the sponge-like property, allows for good nutrient storage. It also binds soil particles. So it actually can improve the soil structure. It's also really useful for microorganisms, creates a habitat for them, food they like, spaces they like. And something I find really cool is just like a dark t-shirt on a hot day, it actually absorbs heat because of its physically darker color. And so it allows for the soil to absorb a little bit more heat. So the last part is our biological component of soil. We're going to talk about what we're talking about is decomposition and fresh residue. These are the parts of the plants that are not alive, but are not quite completely decomposed. And so imagine a forest floor, or we're in fall, so imagine the leaves falling down and then you raked them into your garden bed and they're starting to decompose. This is when plants die back. This is their way of completing nutrient cycling, which is really kind of the big picture of all of this organic matter component. This is why these organic matter, these pieces play such an important role. And although the living organisms part of the soil seems so small, these microorganisms are essential in nutrient cycling. So I just have here two of kind of like the big playing nutrient cycles, the nitrogen cycle and the carbon cycle on the right. But there's other nutrient cycling occurring. I just kind of wanted to highlight these two really big ones. So we have the nitrogen cycle, which converts different forms of nitrogen, which is an essential nutrient for plant growth. And most of this is facilitated by microbes, and it mostly occurs in the soil. And it's because of symbiotic relationships between bacteria and roots and other plants.
The organic matter is also essential for the carbon cycle. It's literally what the organic in organic matter means, is carbon-based nutrients. And so as flora and fauna die, they decompose and return carbon nutrients back to the soil, where plants take them up and microbial activity utilizes it for decomposition and respiration and all of these things. So these nutrient cycles are so essential and kind of like the bigger picture of why it's a growth medium for our plants. And so that's kind of leads us to this whole building up the soil here, is understanding these nutrient cycling, these nature's processes, so that when it comes to new soil formation and their physical properties and their biological properties, that helps us understand. So if you could go to the next slide, Val, thank you. So it really helps us understand, and actually you can go one more. Thank you. This bigger picture. So all of these different pieces, I talked about them in silos, the mineral physical properties, the organic biological properties. I talked about how air and water are affected and all of these things, but they're all really very interacting and impacting each other, and understanding how those things are working and interacting with each other helps us understand how to build our soils. There is one exception here that you may be thinking of. So if you want to go to my next slide, urban soils. It's a very, you might be like, okay, but that's great, but those processes aren't really occurring in my soils anymore. And it's true, in probably in your own landscape, we have really urbanized or disturbed soils. And it's actually a classification of soil that the Natural Resource Conservation Service recognizes, because we know that we've altered our soils in ways that are no longer what they used to look like. They don't exhibit their natural profile. They have these really interesting horizonation going on here. And if you see here on, if you see there's like the lighter layers and then there's a darker layer beneath the lighter one, that dark layer is probably a buried topsoil horizon, probably from construction. And so we see, you know, these variation of soil horizons, we see compaction, we see aeration being restricted because we've compacted them, or and then also there's surface crusting because of that compaction. Because the subsoil layers might be much higher up, we see these elevated pHs. There's also varying soil temperature fluctuations. And then because of the processes, because of culturally what we choose to do with our landscapes, we've also really disrupted the nutrient cycling that's occurring there as well. And so for us, a lot of these issues that we might be having with our soils aren't really about, you know, oh, I have this texture. It's more about what we've done to it. And this image here, I thought it'd be kind of fun to include, because this is actually my front yard. I had to get my sewage pipe replaced after about a year of living in my house. And I already noticed, if you look at the bottom, that's a darker soil down there. That's a buried topsoil horizon. And then much to my chagrin, they didn't separate the topsoil and the subsoil. So when they filled this back in, it was just straight, like it was just straight mixed up. So I'm not trying to say like we screwed up our landscapes, like you're all doing horrible things. I'm saying this is just the nature of the life that we live and the landscape in which we have developed today. And so this is part of what it means to live in the world, and what we do to our soils. And so what I want to encourage you to do is to think of how those soils are naturally formed and to learn lessons from them. So if you hop to the next slide, what we need to be thinking about is our nutrient cycles again. So how are we reintroducing, are we taking lessons from these nutrient cycles that are already naturally occurred, that our ecosystems are already primed to do? And so what are we doing to do that? So next slide. So what we need to do is we need to mimic our natural processes. So as we, a way that we can mitigate the effects of damaging our soils is by mimicking those processes of earth cycles and systems. So when we think of cycling, we want to think of ways that we're returning nutrients back to the soil and completing that cycle that we've broken. So a really simple way of doing that is chopping and dropping as a method of gardening. Chopping the weeds and dropping them on the ground. It's the very plants that are sucking up the nutrients away from the plants we want to grow. And so we're returning them back to the ground to be decomposed. Now, I don't recommend dropping, weeds that have seed heads that are primed to grow. And it does help to know what weeds you are picking up, because if they grow rhizomatously, for example, you might not want to do that one. You might want to compost it instead, for example, which is another practice that returns those nutrients back to the soil. So kind of chopping and dropping informed, I guess. Again, I mentioned composting, so helping that decomposition process along and returning stabilized carbon back into the soil. The same goes with leaving your grass clippings. If you must have grass, then leave the lawn clippings, don't bag them away, leave them. And then that returns those nutrients that your soil took up, or that your grass took up, back into the soil. You don't have to fertilize anymore because your grass is taking away those nutrients. And by just leaving those grass clippings, they're returning back in. You can also mimic nature by building and maintaining a replica of those natural systems. And these don't have to look like crazy prairies or forested ecosystems. They can be maintained and landscaped, but having some kind of deep-rooted natives, reducing the introduced species using those native species, and managing for invasives, and then having just a diversity of plants. We have these large swaths of monocultures of Kentucky bluegrass or whatever grass species we're growing. Having some kind of diversity of native plants is going to help introduce carbon back into the soil. And then the last one is not fighting the site. And I'm going to move through a little quickly because I want to make sure I give you some tools to how not to fight the site. So don't fight the site is really a good summation of listening to your soil and using it as a guide for landscape planning and maintenance. So in order to do this, you need to be able to assess and understand your soil in the first place. This is the same concept as right plant, right place. So don't fight the site, plant the right plant in the right place. So you've learned about the origins of soil, the physical and the biological components. So how can we find that out about our own sites? So next slide. So there's some tools that you can use. Oh, one more slide. I wonder if I didn't save this. There we go. Okay, so there's some tools that you can use. There's the home soil test that costs nothing. Just you have tools at home. And then you can also get some help from lab and research scientists that have a little bit more data to give you some more informed decision making. Next slide. So there's first the jar test. This is where you literally take a handful of soil, you fill up a jar, and then you fill up the jar with water, and then you shake it, and then measuring it at certain times tells you how much sand, silt, and clay is in your soil. Next slide, please. This I actually did with my home soil, and so you can see here, I just filled it up. I measured it, and then if you want to go with one more slide, yeah, that one. That's after 24 hours of letting it settle. And so you can actually see here at the top, there's my clay at the very top. The bottom is my sand. Silt is somewhere in the middle. That tells me the percentages that I have each of those there. And I have a handout for all of you that you can use that I can email out after this webinar. So you can get those resources as well. Next slide. The next one is the drainage test. So this, you dig a hole 12 by 12 inches. It tells you, you fill that hole with water, you let it saturate. And then the next day you come back, you fill it with water again, and you measure how quickly the water drains every hour. And this kind of tells you how well your water is draining. And this tells you a little bit more, because if you find out, we have urbanized, if we have an urbanized soil, this might tell you, well, yeah, I have a good silty soil, but my drainage sucks. I wonder what else is happening here. So it gives you another tool to understand, you know, how well what's happening with the water, which is such an important question. The next slide tells you a little bit more about soil testing. I love the new Lawn to Lake Midwest website. It's so many good resources, not just for lawns, but for just managing your landscapes in general. And this one allows you to look at soil testing sites that are close to you or where you can send them to. And I recommend getting one that accepts a homeowner sample. If you live in an urbanized environment, get a heavy metal test. It's a little bit more expensive. Normal regular soil tests are like $30. I think this might add like another 10 to 20 on top of it. But it's good to know that, especially if you're working in your garden, in your yard, if you have heavy metals there, so you can do something to mitigate that. So I always like to say, like, try and do that if you can. And my last slide, next slide. The last one for webs, for soils assessment is using the Web Soil Survey. This is a free tool to you. It's less intuitive, but it is really, really neat. Before I bought my house, I used this tool to figure out, you know, am I going to have issues with the flooding in my crawl space? And this is a tool that can tell you a little bit more than what's going on than like a foot below the ground. It might tell you what's happening 5 feet below the ground, or 6 feet. And it tells you historically what's been done to that landscape. And so I included some resources as well about this assessment to help you understand, you know, a video that walks you through it as well as a handout. Last slide. So here's my summary slide. Thank you for bearing with me. I'm sorry I'm going a little bit over with the tech issues and things like that. But to kind of leave you with some, like, what's the bigger picture here? So our origins and the physical and biological properties, they really do influence each other. And understanding these things are going to give us a lot more insights into what's happening beneath our feet and what we can do to replicate those processes. Disturbed soils, they do have this disrupted soil formation, and we've disrupted the nutrient cycling processes. And so that's a fundamental thing we need to understand in order to build up our soils, because we need to mimic these natural processes so we can help complete the cycle. And then we can learn more about our soils through really easy and accessible tools. We can do testing at home. We can do testing relatively cheap, and these are all very accessible to us. So that's all I have on soils. Thank you everyone again for bearing with me. I have the evaluation up here. I wanted to do just a quick plug for next month's webinar. Looks like they're going to be talking about the Winter Night Sky Tour, which I think is going to be really, really exciting. So go ahead and check that out on the Everyday Environment website. Val, if you want to go to the next slide, there's my email at the bottom. It's aeg9@illinois.edu. Feel free to send me questions specifically about your soil if you have questions that are more specific for the group, or if you didn't get a chance to ask because of all these tech issues. I really appreciate it. So I hope you all feel a little bit more passionate about soil and appreciative of what's going on beneath your feet. And I hope you start implementing some of those processes that I talked about at the end there. Thank you so much.
Thank you for tuning into CUWise TV. We hope you enjoyed the show. This video can be accessed anytime on youtube.com. In the YouTube search bar, type in UPTV6 and look for their microphone logo. We hope you will join us again next week for more local, engaging content designed specifically for Champaign County older adults. Take care and stay safe.